Hello my dear students. So I am going to continue with the 16th lesson of your grade 10 science textbook. So in the previous chapters, we looked at different types of changes. The physical change, chemical change. Then as chemical changes, we looked at many different chemical reactions. So in a chemical reaction, you know from reactants, products are formed. And this takes place in different ways. So that's why we have 4 different types of chemical reactions: the chemical combination, the chemical decomposition, single displacement and double displacement reactions. So thereafter, we discussed how we can write balanced chemical equations for these chemical reactions. So in this chapter, I am going to discuss reactivity of metals. So metals react with different substances. You're familiar with metals, you're familiar with their physical and chemical properties. We have discussed some examples for metals as well. So there we are going to consider the reactivity of metals with different substances. So the first one, reactions of metals with air. So when we say air, students, what are the components of air? You all know that there is nitrogen, then there is oxygen, there can be a small amount of carbon dioxide, there is water vapor, and there are some noble gases. So nitrogen, oxygen, carbon dioxide, water vapor and noble gases. Out of these, when we say reaction of metals with air, we mostly consider oxygen, because that is the most reactive one. When you burn something, oxygen in air is needed for the combustion. So oxygen in air reacts with metals. Same way, even nitrogen can react. Carbon dioxide can react with certain substances, but mainly we consider oxygen. Now this is seen in our day-to-day life also. We see many examples. Now look at these two pictures. Now this is gold jewelry. Then here you can see iron nails. Now iron nails, when you buy from the shop, initially they are very shiny, they are not rusted. But when you keep them for some time, a few months, then you can see the rusting of iron. So now here you can see it has rusted. The color changes, the nature changes, the shine is lost. But if you look at gold, it is the same way. That's why we mostly use gold jewelry. So their shine is not lost. The lustrous nature of metals is not lost for gold. Same goes for metals like platinum. Their shine is not lost. But you remember seeing magnesium in the lab. Magnesium strips. When you buy the strips, they are shiny and nice. But when you store it for some time, they get tarnished. You get an oxide layer. So that's why every time before we do the activity, what do? We clean the magnesium strip with sandpaper. After we clean it, you get the shiny, lustrous nature of magnesium. So like that, there are different metals we use in our day-to-day activities as well as in the laboratory, and they react in different ways. Some don't react. Metals like gold, platinum, they don't undergo any change. They remain the same. But metals like iron, magnesium, they undergo changes. So that is what we are going to discuss in this particular topic. Reactions of metals with air. So as I told you, mainly oxygen. We have seen that the objects such as nails, barbed wire and cutting tools, you all know what those are. The picture shows some nails, then barbed wire, what we use to make fences and all. The barbed wire and cutting tools. There are many tools, even scissor, the blade is made up of iron, knife, like that. There are many cutting tools. Even the cutlery, iron, steel, but they can rust to a certain extent. Steel, stainless steel, doesn't rust very quickly, but normal iron, you have seen it rust quickly. But jewelry made of gold do not tarnish even after a long period of time. So, they do not tarnish even after a long period. You know the meaning of tarnishing. The losing of shine of metals, that is tarnishing. Have you inquired into the causes for this difference? So, that is what we are going to do now. You can have an answer for this by studying how metals react with air, water and dilute acids. So, here we are going to consider air, water and dilute acids. Different types of reactions of metals. So, we said reactivity of metals. Under that, now I am going to discuss reaction of metals with air. So, with that students, I will move on to the next slide. Activity. Investigate how metals react with air. So, how metals react with air. To do that, we need these two materials, the required materials. Here you can see this is sodium metal. Sodium metal. And here we have magnesium metal. Magnesium metal. So, you can even write it as sodium and magnesium. So, you all know how we have sodium in the lab. We have observed sodium before also. It's usually stored in a glass bottle, a brown color glass bottle or even a plastic bottle that is not transparent. And inside that there is kerosene or paraffin. Inside that only we have sodium. So, you take that out and we need to use that. But magnesium, the strip is stored in the lab as it is. So, as you know, initially when you look at the magnesium, normally there is a layer of oxide over magnesium, the magnesium oxide layer. And normally we clean it with a sandpaper and we observe the magnesium strip. So, let's see how we can investigate how metals react with air. So, the method is this. Expose the freshly cut piece of sodium and the cleaned 2 cm magnesium ribbon to air. So, freshly cut piece of sodium, that's important. When you take sodium out of kerosene or paraffin from the container, when you look at the surface, initially it's coated with paraffin, sometimes you have to remove that coating, and then if you look at the surface, students, it's not shiny. You need to observe the new cut surface, that is freshly cut piece of sodium. Then you will see how it looks like. At the same time, we need to use cleaned magnesium strip. So, to clean the magnesium strip, we all know we need to use sandpaper. You take the magnesium strip that is there in the lab and you need to nicely clean it with sandpaper. So, you observe both of them. Then, observe well the cut surface of the piece of sodium and the magnesium ribbon. Record your observations. So, when they say observe well, you need to keep it for some time. Say 10, 15, 20 minutes, even half an hour, you can leave it and observe it. There you will see a change or there may be no change. From that only, we can decide how these metals react with air. So, a very simple activity, you need to have a clean piece of magnesium. We need to get a freshly cut piece of sodium. Keep it on 2 watch glasses and you need to observe them for some time. So, since this is a very simple activity, let us go to the lab and do the activity now. Okay, students. So, now we are trying to understand the reactivity of metals. Under that, the reactivity with air. So, to do that activity, I have these materials. You can see the magnesium tape here. You have already seen this before also. I have already cleaned the magnesium tape. So, there are a few pieces of magnesium tape and here, this is how you can store the sodium in the lab. We have discussed before, students, sodium is a very reactive metal. When we discussed about metals, it's a reactive metal. So because of that, we normally store it in paraffin or kerosene. And usually it is kept inside a glass brown colored bottle so that light doesn't penetrate into the bottle. But here we use a plastic bottle. Here also light doesn't go into the bottle. So inside it has been stored in paraffin. So from the bottle I have taken a few pieces of sodium here. You can see the paraffin also, students. If I move it, you can see it is kept in paraffin so that it won't react. So what we need to do is we need to compare how both magnesium and sodium react in air, how fast the reactivity takes place. Now even while I am talking, you can see there's no change in the magnesium strip, but just to compare, we will look at the magnesium strip. With that, I will compare the piece of sodium. So I will take this piece of sodium here and I'll place it on the filter paper and I can cut it. This piece of sodium I have already cut it. If you can observe, here can you all see the shiny surface, the freshly cut surface. Observe it clearly. Can you all see the shiny surface there? So from that also you all know sodium has the luster, the shine, but observe it closely. You can see that, students. With time, what happens to the shine of the surface? When it was freshly cut, it was very shiny. At the same time, if we take a piece of magnesium and compare, here you can see the same time we have the magnesium exposed to air, but look at the surface of sodium. You all can see the tarnishing of sodium very quickly. You all know what tarnishing is, losing of the shine. Now already it has become a little bit dull compared to the previous shine, but still the magnesium is the same. So we will need to observe it for a little time. Still we can see the shine, but you all can observe, students, the shine is decreasing with time. Even on this surface you can see, in both surfaces you can see. We will compare sodium and magnesium. So students, you all were able to see the tarnishing of sodium. Just to make sure that it reacts with air, what I will do is I will cut this piece into two other pieces again. So here you can see the shiny surface. What I will do is I will put this piece into oil. So here, students, observe this surface. It is shiny. That is part of the sodium I cut from there. Here again you can observe the shiny surface. Now this piece that is stored inside paraffin is not exposed to air. But here this piece is exposed to air. So we can compare and confirm that the sodium reacts with air or oxygen in air. At the same time, I showed you all the magnesium strip. Still the shine is there. So that means the reactivity of magnesium with air or with oxygen is comparatively less compared to sodium. So still you can observe the change here. If you look at this surface, the previously cut surface, you can see it has completely tarnished. You cannot see the shine there. And this also with time, you all are able to observe the decrease in shine, the tarnishing of sodium, because it reacts with oxygen in air. At the same time, if you look at this piece, still you can see the shine. So from these observations, students, now we had the magnesium strip, a clean magnesium strip. Still it is exposed to air. There is no change in the color or the shine. Shine is still there. You can see it is still shiny. But when I took the sodium from paraffin and when I cut it, you saw the freshly cut surface, it was very shiny. But you all can see now here, students, both the surfaces, the exposed surfaces exposed to air or oxygen, they are not shiny anymore. So that means sodium reacts very fast with oxygen in air, whereas magnesium compared to sodium reacts slowly with oxygen in air. That is how we compare the reactivity of metals with oxygen or reactivity of metals with air. Both are same because usually the metals react with oxygen in air. So when we say reactivity of metals with oxygen or reactivity of metals with air, it's basically the same reaction. So I'm sure you all can understand that now. Okay, students. So did you all observe clearly what happens to sodium and magnesium when they are exposed to air? Yes. So initially when I took the piece of sodium out of kerosene, the surface was not shiny. But when I cut it, the freshly cut surface was shiny. But when I kept it aside, within few minutes, you were able to observe that the shine was lost and it became tarnished. It became dull. So there, the reaction of sodium with air was very, very quick. Within few minutes, you were able to see the change. But we took the cleaned piece of magnesium. You were able to see the shine. We kept it aside. Nothing happened to the shine. So within that short period, there was no reaction between magnesium and air. So from that, what can you understand? Sodium reacts faster with air, whereas magnesium does not react fast with air. Or you can say it reacts slowly with air. Because you know, normally when you store magnesium in the lab, it does react with oxygen, that is air, oxygen in air, and it forms the oxide layer. That is why we need to clean the surface before each reaction. So it does react, but it reacts slowly. So we need to write the observation and the conclusions. So observation, freshly cut surface, of sodium was shiny. Shine was lost quickly when the sodium was exposed to air. Cleaned surface of magnesium was shiny. Then shine was not lost when exposed to air. So those were the observations we got. Then the conclusion. Sodium reacts fast with air. Magnesium reacts slowly with air. So the observations, freshly cut surface of sodium was shiny. Shine was lost quickly when the sodium was exposed to air. Clean surface of magnesium was shiny. Shine was not lost when exposed to air. So this is for magnesium. From that we can conclude and say sodium reacts fast with air, magnesium reacts slowly with air. You are familiar with these two reactions also, students. We have written the balanced chemical equations as well. So here if I write the balanced chemical equations, sodium, as I told you, this is not part of the conclusion. This is to recall what we have already discussed. So sodium reacts with oxygen in air and forms sodium oxide, Na2O. You all know this is a chemical combination reaction. How do we balance that? We need to balance oxygen. So we will put a 2 in front of sodium oxide. That is the coefficient 2. So then to balance sodium, we put the coefficient 4 in front of sodium. So 4 sodium reacts with oxygen forming sodium oxide. This is a very fast reaction. Fast reaction. Then we had the reaction of magnesium with oxygen giving rise to magnesium oxide. Is this fast? No. It is a slow reaction, comparatively slow reaction. Is it balanced? No. We need to balance it. Magnesium is balanced. Oxygen, we need to put 2 as the coefficient in front. To balance magnesium, you put a 2 in front. So I am not going into detail about balancing equations because I have discussed that in the previous chapter. So you all know how to balance it. So these are the reactions taking place. Sodium reacts quickly with air, that is oxygen in air, forms sodium oxide. Magnesium reacts slowly with oxygen in air and forms the magnesium oxide layer. Is that clear to you all? So with that, students, I will move on to the next slide. When burnt in air, metals like sodium and magnesium react with oxygen to form their oxides. So I have written the equations before. Here, although we say burnt in air. Now note these, students, we say burnt in air. Metals like sodium and magnesium react with oxygen to form their oxide. So here, since sodium reacts very fast with air, we don't need to burn it. So you have to remember that. Sodium reacts when exposed to air. And also you're familiar with the reaction where we have burnt magnesium. We have done that before in one of the previous chapters. We burn magnesium. It burns with a bright white flame. So when burnt in air, magnesium will react with oxygen. So again, if we write the two balanced equations, you can remember those, students. I already did it. Sodium plus oxygen gives rise to Na2O. So to balance, we do it like that. 4 sodium plus oxygen gives rise to 2 Na2O. That's the balanced equation. The same way, magnesium plus O2 gives rise to MgO. So 2 MgO and 2 Mg. So those are the two reactions, oxygen and magnesium, and the reaction is fast. Then, if we look at other metals, now we use zinc, we use iron, we use copper. these metals also have a shine. They have the lustrous nature, and when they are exposed to air, they don't immediately react with oxygen. But when you heat them for a long time, and that also has to be strong heating, then what happens is, and for a long time, you will see the color will tarnish. The shine will be lost. So when heated in air, the surface of metals like zinc, iron and copper. Zinc, iron and copper becomes dull. Prolonged heating turns them into the oxides. If you heat it for a long time, and usually it's somewhat high temperature, then of course they react with oxygen and form the oxide. As an example, I will write the reaction of zinc with oxygen. So here zinc, that is the metal, reacts with oxygen in air, forming zinc oxide. You all know the valency of zinc is also 2. So ZnO. We need to balance this as well. To balance oxygen, you put a coefficient 2 in front of zinc oxide. Then to balance zinc, you put a 2 there. You are familiar with balancing equations now. So 2 zinc metal reacts with O2, giving rise to 2 zinc oxide. That is when there is prolonged heating. This is important. Prolonged heating. So now can you see? Sodium reacts when exposed to air. Magnesium has to be burnt in air, but then on burning it reacts quickly. But if you leave it aside, it takes few days or even weeks. But here, zinc, iron and copper, they do react, but you need to heat them for a long time. Then the color tarnishes, the shine gets lost. But then prolonged heating turns them into oxide. But you might think, students, now iron in the first slide we said it undergoes rusty. That is also a reaction, a chemical reaction, but that occurs slightly differently. It's not the reaction with air. And for rusting, it does take a long time. You all know that. So here, of course, we are looking at the changes immediately. While heating, what happens? The same way, if you take metals like silver, platinum and gold. You are familiar with all the standard symbols. Silver Ag because it's argentum, platinum Pt and gold Au, aura. So metals like silver, platinum and gold are not converted to their oxides even when strongly heated. They are not converted to their oxides. That is why you all know when they make gold jewelry, they heat gold. And when they heat gold, it does not react, but it melts. So you have the molten gold, the liquid gold, that is converted into gold jewelry. So that's possible because even on strong heat, these metals don't react with air. That is oxygen in air. So now you all can see a difference. You all can understand that the metals react differently with air, or for that matter, react differently with oxygen in air. Based on these facts, it can be concluded that metals differ in their readiness of reacting with oxygen. So, if we consider it as a summary. Now, sodium with oxygen very fast. Then magnesium with oxygen, we can say burns. Then we said iron, copper and zinc. These with oxygen react slowly. And gold, platinum and silver. These three, silver, platinum, gold. It can be in any order. Here I am just writing a summary. Plus oxygen, strong heating, still no reaction. Is that clear to you all? Sodium reacts very fast. As you expose it to air, it tarnishes and reacts. Magnesium, burning it exposed to the flame, it burns quickly. Doesn't take a very long time. Within few minutes, it burns off. Whereas iron, copper, zinc, you have to heat it, prolonged heating. So here, prolonged heating. Prolonged heating. They react slowly. But silver, platinum and gold, all three, even if you heat them strongly, there is no reaction. So you can see there is difference in their readiness to react with oxygen. You have to remember this, student. And for these metals, you need to remember their products and you need to know the balanced chemical equation. Okay, students. So you observed how sodium reacts with air. When you expose it to air itself, it reacts. Magnesium burns with oxygen, giving magnesium oxide. When you heat iron, copper and zinc, the color tarnishes. The shine is lost. That's all you were able to see. But only on prolonged heating, they will react. But we could not see them. At the same time, this of course does not react. We didn't do these activities, but they don't react. So that is how the reactivity changes, or the readiness of reacting with oxygen differs from metal to metal. You all have to remember that, students. So with that, I will move on to the next slide. Reactions of metals with water. This is the second type of reaction. How metals react with water. So some metals react with cold water, hot water and water vapor. So cold water, hot water, you all know. The difference is the temperature. Normal room temperature water is also considered as cold water or even very cool water. But normally we use the room temperature water, and hot water you have to heat the reaction mixture. You take water, you have to heat it and you need to observe how the metals react with hot water. Then water vapor. When water boils, steam is released. So that is water vapor. And you all know, students, water vapor has more energy than boiling water. We will discuss that in more detail later, but you all know this. You have to remember, steam or water vapor has more energy, more heat energy than hot water or even boiling water. So there are some metals that do not react with cold water may react with hot water. The ones who do not react with cold water and hot water may react with water vapor because it has more heat energy. So that is why we need to consider all three instances. Cold water, hot water, both are liquid states. Water vapor, it is in the gaseous state with more energy. So cold water, hot water and water vapor at different speeds. Hence, the reactivity of metals towards water differ from one another. So, the metals react differently with water, and that also three different instances, and they react with different speeds. To understand that, we will do this activity. The first activity is to observe reaction of sodium with water. Activity, reaction of sodium with water. To do that, we need these materials. We need water. We need a trough. When we say trough, it has to be a somewhat broad container. You all know what a trough is. If you can't find a trough, you need to have a glass container. It has to be broad so that you can take a large volume of water for even a small amount of sodium. Then we need the sodium metal, and also we will need red litmus paper. In addition to that, in our activity, when I do the activity, I will be using the indicator phenolphthalein. So we need phenolphthalein indicator. Phenolphthalein indicator. I hope you all are familiar with phenolphthalein indicator. This is a colorless liquid and it gives a pink color when it is exposed to alkaline substances or bases. Alkalis or bases. So it gives a pink color when there is a base or an alkaline substance. So these are the materials that are needed. What we will do is we will take a trough. Into that we take a large amount of water. Into that we take a freshly cut piece of sodium from the container. It can be a brown color glass bottle. Inside that it will be stored within paraffin or kerosene, or a plastic bottle containing paraffin or kerosene. Within that sodium will be stored. So just before the activity we need to take that out. You need to cut tiny pieces of sodium and we need to put it into this trough containing water. So before doing that, if we are using phenolphthalein indicator, we can put a few drops of phenolphthalein indicator before we put sodium, or we can put it after. Either way is okay. We just need to observe the color change. So then we use the red litmus also to test the solution after the reaction in order to confirm the products that are produced. So then I will move on to the next slide where I discuss the procedure again and then we will do the activity. So the method: add a small piece of sodium the size of a seed of a green gram, a very tiny piece of sodium, to the water in the trough. Record the observations. So in addition to that, we can add a few drops of phenolphthalein indicator to the water, and also test the water in the trough after the reaction with sodium is completed with a strip of red litmus. So add a few drops of phenolphthalein indicator to the water. That is also, you can, as I said, you can do it before you put sodium or you can put it after you react sodium with water. Test the water in the trough, that is after the reaction is completed. After the reaction with sodium is completed with a strip of red litmus. So there also you might be able to see a color change. So those are the steps of the activity, students. This is only the reactivity of sodium with water. So we will go to the lab and do this activity now. Okay, students. So now I am going to do this activity where we will observe the reaction of metals with water. So to do that, I have the first activity where we observe the reaction of sodium metal with water. So you have already seen, I told you all, sodium metal is very reactive. Because of that, we store it inside the plastic bottle. In that also there is paraffin liquid, or you can use kerosene liquid. Inside that only we store sodium. So earlier you all saw I took out the piece of sodium, then we cut it. You saw the quick reaction with air. Now what we will do is, again I have a very small piece of sodium that I have to again cut it into a tiny piece, and then I will be putting it into water here. So when the reaction takes place, that is when sodium reacts with water, there will be two products produced. You need to observe them. To observe the formation of one product, what we will do is, we will add this particular indicator, phenolphthalein indicator. Now this is an indicator with a basic medium. Now this is a colorless indicator, colorless solution. Here you all can see, students, colorless solution. But in the presence of a base, it will become pink in color. So what I will do is, first I will add a few drops of phenolphthalein into water so that you can observe the change very easily. So I have water inside a trough. We need a very large container because you will see the reaction is very vigorous. Because of that, we need to have a large amount of water in a large container. So this is a trough with water, and I'll be putting a small piece of sodium. Before that, as I told you, I have added few drops of phenolphthalein, and also I have this litmus paper. You're familiar with these, students, litmus paper. Again, red color litmus paper changes color to blue when in contact with a basic solution. So we will test with this also after the reaction is complete. So now what I will do is, I will take the sodium, cut a small piece of sodium from this what we already have, and I will put that into water. You all need to observe clearly how the reaction takes place. Can you all see the sodium moving around, and you all can hear a hissing sound? It moves around, it darts around because of the hydrogen gas evolves and it pushes the sodium here and there. You can see how fast the reaction is, and you can see the appearance of pink color. As I told you all, that is because of the base that is produced. So now see, within a very short time, the sodium completely reacted with water. So from these observations, students, what were the observations you all got? You saw that the sodium darts around, it moves around on the surface of water. So it floats on water. From that you all can understand that sodium is less denser than water. You have discussed all these before also, but just to recall what you have studied. So it's less denser than water. It's very, very reactive, or we say the reaction is vigorous, because you saw the movement of sodium. It was very quick. The reaction completed very quickly. And here we took a large amount of water, and you saw the appearance of this pink color. So here in the reaction, sodium reacts with water and forms sodium hydroxide and evolves hydrogen gas. So I told you all, you get a hissing sound. That's because of the evolving of hydrogen gas. And because the gas pushes the sodium around, that's why it moves around also. And then the pink color of phenolphthalein is due to the presence of sodium hydroxide. Sodium hydroxide is a base. So I told you all, the phenolphthalein indicator gives a pink color with bases. And to confirm that, I have this litmus paper, red color litmus paper. Now if I dip this in this solution, you all will be able to see paper. The red litmus turns to blue in color. So here if you dip the litmus paper, the color will change. So here we have to dip the litmus paper in it and then the color will change. So when we hold it for some time, students, now you saw it was only a small amount of a very tiny piece of sodium that I put, but with the indicator, since I put a few drops, additional drops, it showed the color quickly. But for this to change color, we need to keep it for some time. So here you can see, students, now the litmus paper has become blue. The red litmus paper turns blue in color when exposed to a base. So sodium hydroxide, as I told you, is a base. So because of that only, the red litmus turn blue. So from that observation also, we can confirm that the product, when sodium reacts with water, one is the evolving or liberation of the hydrogen gas, and the second product is sodium hydroxide. We confirm that it is sodium hydroxide using phenolphthalein indicator and the red color litmus paper. So that is the reaction of sodium with water, a vigorous reaction which evolves hydrogen gas and forms sodium hydroxide solution. Sodium hydroxide is a base and it is a vigorous reaction. The sodium floats on water. It darts around the surface of water and also you were able to hear the hissing sound, the releasing of hydrogen gas. So those are the observations of this reaction. Okay, students. So did you all observe what happened with sodium and water? Yes. When we put the piece of sodium into water, the first thing you all observe that sodium floats in water. Why is that? Because the density of sodium is less than that of water. That is of course a physical property, but you do observe that during the reaction. When did the sodium stay in one place? No. It darts around on the surface of the water. So it darts on the surface of the water and it reacts. When reacting, I told you all, I can hear the hissing sound. You all also would have been able to hear the hissing sound. And if you observe closely, you can observe the evolving of gas. But that is of course not very clear. But you can see when it darts around, the size of sodium decreases and the reaction completes very quickly. Within a few minutes, the reaction is complete. Then you were able to see the phenolphthalein. I showed you all it's colorless and we put it into the trough, the water into the trough, and there you were able to see when sodium reacts with water, you were able to see the formation of pink color. And I told you all, this pink color confirms the presence of a base or an alkaline substance. So here, when sodium reacts with water, sodium hydroxide is formed. That is a base. That is why we get the pink color with phenolphthalein. And also the darting of sodium on the surface, and that is due to the liberation of a gas. And what is that gas? It is hydrogen gas. So the products when sodium reacts with water are sodium hydroxide and hydrogen gas. We did another step. We tested the water in the trough using red color litmus paper. What happened there? The red litmus turned blue. Again, you all know, students, the turning of red litmus to blue is due to the presence of a base. So that also confirms that a base is produced. So sodium hydroxide is produced when sodium reacts with water. So those were the observations, and from that we can conclude and say sodium reacts fast with water and produces sodium hydroxide, which is a base, and liberates hydrogen gas. Is that clear? So we will write down the observations and conclusions. Observation: sodium darts around on the surface of water. Hissing sound. Sound is heard. Solution turns pink with phenolphthalein. Red litmus turns blue when tested with the solution. Or we can say that solution turns red litmus to blue. So sodium darts around on the surface of water. Hissing sound is heard. Solution turns pink with phenolphthalein. Red litmus turns blue when tested with the solution. So all these observations, and the reaction was very fast. Now we took a very large amount of water. We took that big trough, and in that you saw there was a large volume of water, and we put a very tiny piece of sodium. So that itself is a very fast reaction. What if you had a small amount of water and you put a big piece of sodium? It can start burning, it can catch fire, and it can be an explosive reaction. So that means the reaction of sodium with water is a vigorous reaction. We use the term vigorous reaction. So to prevent accidents occurring due to this vigorous reaction only, we take a large trough containing a lot of water, and also we take only a small piece of sodium. Usually during this reaction there is lot of heat evolved. Now since we take a large amount of water, we don't feel the heat that much. But if you took small volume of water and put a piece of sodium, then of course you will feel the heat, the beaker becoming very warm. But as I said, to avoid accidents, we use the large trough with a large volume of water. So in this reaction, heat is also evolved. So you see the evolving of or liberation of gas is there, then darting around of sodium on the surface, and also heat is evolved. So those are observations that confirm the chemical reaction taking place. So from that, we can conclude. What is the conclusion? Sodium reacts vigorously with water. In other words, you can say reacts very fast with water. And produces sodium hydroxide that is a base or alkaline solution and liberates hydrogen gas. So those are the products. So you know the reactants, sodium and water. You know the products, sodium hydroxide and hydrogen gas. So can you all write the balanced chemical equation? I am sure you can. So how do we do that? Sodium with water will give rise to NaOH plus H2. So we need to balance the reaction. You can remember I said we do this in a slightly different way. What do we do? Here we have 2 hydrogens. We have 1 and 2. There are 3 hydrogens. So to balance that, what do? We put a 2 in front of sodium hydroxide. The coefficient 2 is written in front of sodium hydroxide and also a coefficient 2 in front of water. Again to balance sodium, we put a coefficient 2 in front of sodium. So 2 sodium, 2 water gives rise to 2 sodium hydroxide and hydrogen gas. That is the balanced chemical equation. A very fast, vigorous reaction. I am sure you all can understand that. With that, I'll move on to the next slide. The piece of sodium darts on the surface of water swiftly with a hissing sound. So you have to remember this. The piece of sodium darts on the surface of water swiftly with a hissing sound. So hissing sound is due to the evolving or liberation of hydrogen gas. Darts around because of the vigorous reaction. It has to move around. If it was still, it can lead to explosion. The piece of sodium which is small catches fire if it stays motionless. So it can be explosion or it can catch fire. Catches fire if it stays motionless. The red litmus paper in the trough turns blue. So that confirms the presence of a base. Same thing can be confirmed with phenolphthalein. Phenolphthalein turns pink. Sodium reacts violently with water, liberating hydrogen gas. So vigorous reaction or violent reaction. Turning red litmus to blue shows the formation of an alkaline or basic solution. What is that? That is sodium hydroxide. Alkaline or basic solution. You have to remember this. Now we will be discussing about bases, acids and all those different substances in grade 11. But you all have to know this is an alkaline or basic solution. So from that, we can get the equation. What happens here is that sodium reacts with cold water. You have to remember that. Reacts with cold water, giving sodium hydroxide, a basic solution and hydrogen. So now you know to write the balanced chemical equation as well. Sodium plus water gives rise to NaOH plus H2. So how do we balance it? You need to have 2 here, a 2 there and a 2 there. So you put the coefficient 2 in front of sodium, water and NaOH. So 2 sodium, 2 water gives rise to 2 sodium hydroxide and hydrogen gas. That's the balanced chemical equation. What type of a reaction is this? You are familiar with that also. Sodium displaces hydrogen from water. So single displacement reaction. Now you should be able to relate all these, students. We have learned the types of reactions. You know to balance the reaction. Now we are looking at the reactivity of metals. So you need to write the balanced equation as well as you need to identify the type of reaction. I am sure you can do that. So with that, students, I will move on to the next slide. Again an activity. Now we are comparing the reactivity of metals. So we did the reaction of sodium with water. Now the reaction of magnesium with water. So the activity reaction of magnesium with water and the required materials. So here of course we can use a beaker. We can even use a boiling tube. Beaker, or you can use a boiling tube. Why a boiling tube and not a test tube? We will need to heat this water. Water with magnesium metal needs to be heated as well. So we can't use a test tube. We have to either use a beaker or a boiling tube. Then we need water, and we need magnesium. So these are the materials, a simple activity. We will discuss the procedure first. Method. Put the clean magnesium ribbon into the beaker of water. You all know why we need to clean the magnesium. Normally when it is stored in the lab, what happens? It reacts with oxygen slowly. Now you know that. It takes time, but there is reaction and the magnesium oxide layer is formed over magnesium. So when you clean it with sandpaper, the oxide layer is removed, the magnesium metal, the lustrous shiny metal is exposed out. So we need to have cleaned magnesium ribbon into the beaker of water. So you take a small beaker, take water into it, and into that you put the clean magnesium ribbon. And you need to record the observation. You need to observe it for some time to see whether it reacts. If it reacts, how it reacts. If not, whether it reacts or not, what we do is we heat the beaker of water with the burner. Using the Bunsen burner and the tripod with the wire mesh, you can heat the beaker of water. Otherwise, if you use the boiling tube containing water and the magnesium strip, you can heat it directly on the Bunsen flame. So either way, we need to heat the water and then you need to record the observations. So here we will be looking at the reaction of magnesium with cold water. So I told you all students, we discussed it before. There are three instances: cold water, hot water and water vapor. Now sodium, it reacted violently with cold water. So we don't have to think about heating it. That will obviously be a violent reaction. So we did not try it. But here we will be using cold water, and when we heat the beaker, we will be observing the reaction with hot water. So two instances. We can also try with steam, but in this activity, I'll be reacting magnesium with cold water and hot water. We will observe what happens. So again, a simple activity. I'm sure you all have understood the procedure. We will go to the lab and do the activity now. Okay, students. So now we are trying to understand the reaction of metals with water. In that, I showed you all the reaction of sodium with water. You all were able to observe that it was a vigorous reaction. Now we will see how magnesium, another metal, reacts with water. So you are already familiar with magnesium. It is available in the lab in the form of strips, and normally you all know. Now here in this strip, I have cleaned most part of the strip, but here and there you can see the oxide layer. So what do? We use a sandpaper and we clean it completely so that you can see the luster and the metal will be completely exposed. So then we can carry out the reaction. So first what we will do is we will take a certain small amount of water into a boiling tube, and into that I will put a piece of magnesium strip. We will observe what happens. Then what I will do is I will heat the boiling tube with containing water and the magnesium strip, and then we will observe the reaction taking place. So I will take a small amount of water into the boiling tube. And then we'll put a few pieces of magnesium. I'll put 2 pieces of magnesium into this. This is cool water or normal temperature at room temperature. So here you all can see the magnesium usually sinks in water. The reason you all know magnesium is more denser than water. We did the reaction of sodium with water. You saw the sodium floats on water. But here magnesium sinks in water. And if you observe closely, can you all see any change there? Look at the magnesium strips. Do you see any change? Can you see any change there, students? Is there any reaction taking place? So there was no change. So you don't see any change taking place. Even if we keep this for a long time, still we won't see any change. The reason is magnesium does not react with cool water. Or even for that matter, magnesium does not react with room temperature water. So what we are going to do next is, I am going to heat this boiling tube containing water and magnesium. So then you will be able to see the change. Boiling tube, since it's a boiling tube, I can directly hold it to the Bunsen flame. You all know that. And normally when we heat the solution, we have to make sure that we don't have the boiling tube directed towards our side. It has to be away from us. And normally you all shouldn't stand in front as well. So now you all have to observe carefully, students. When I heat the boiling tube with water and magnesium. We have to heat it for some time. Now maybe you all can observe a change. Can you all see the gas bubbles around the magnesium strip? So when you look closely, you can see the gas bubbles. So the reaction is starting. I will hold it to the flame for some more time. Now you can see the water also starting to boil. So with that, if you look at the magnesium strip, if you look at it carefully, you can see the gas bubbles. So here students, you all can see the gas bubbles around the magnesium strip. Can you all see it clearly? So you can see that. So from these students, what can we understand? You all can understand that magnesium reacts with hot water. It did not react with cool water. Magnesium doesn't react with cool water, but it reacts with hot water. And when it reacts with hot water, magnesium evolves hydrogen gas and also magnesium hydroxide is formed. So the reactants are magnesium and water. The products are magnesium hydroxide and hydrogen gas. So earlier also we did an activity where with sodium there we used phenolphthalein. You all know why we use phenolphthalein. If there is a base in the medium, then phenolphthalein becomes pink in color. So the same thing can be done with this as well. So since this is magnesium hydroxide, that is also basic in nature. So what I will do now is, I will put a drop of phenolphthalein to observe whether a base has been formed. That is, magnesium hydroxide has been formed. So I will put a drop of phenolphthalein. Then you will be able to see a color change. So now can you all see, students, the appearance of pink color. So although this is not part of the activity, I just use the phenolphthalein to confirm that magnesium hydroxide is there in this reaction mixture. So when magnesium reacts with hot water, the products are magnesium hydroxide and evolving of hydrogen gas or liberation of hydrogen gas. So those are the products. You can see the pink color and also you can see the hydrogen gas bubbles around the magnesium strip. You all can see the gas bubbles clearly and the pink color. So that confirms that magnesium reacted with hot water. Okay, students. So we did two activities or two parts of the activity. We took magnesium in cool water. You saw there was no reaction. So magnesium does not react with cool water. But when we heated the solution, you saw the reaction, liberation of hydrogen and the formation of magnesium hydroxide. So magnesium reacts with hot water and forms magnesium hydroxide and liberates hydrogen gas. So those are the reactions of magnesium with water. In addition to that, magnesium can also react with steam. When it reacts with steam, it will produce magnesium oxide and liberate hydrogen gas. So sodium reacts only in one way, vigorously with water. But magnesium reacts in different ways. With cool water, there's no reaction. With hot water, it produces magnesium hydroxide and releases hydrogen gas. With steam, it produces magnesium oxide and hydrogen gas. So you all have to remember those three reactions. Okay, students. So you all were able to observe clearly what happens when we put a piece of magnesium strip into cold water, that is beaker containing normal water. Was there any change? No. So magnesium did not react with cold water. So there's no reaction, that is why we didn't see any change. But when I heated the magnesium with water, what did you all see? You were able to see the liberation of gas bubbles. So here again, the gas liberated is hydrogen. So then magnesium reacts with hot water, liberates hydrogen gas, and also magnesium hydroxide is produced. So that also can be tested with phenolphthalein. If you put a few drops of phenolphthalein into the container, beaker or the boiling tube, you can see around the magnesium strip you will get a pink color. That again will confirm the presence of a basic substance. So magnesium hydroxide is also a basic substance. So magnesium does not react with cold water. It reacts with hot water and produces magnesium hydroxide and hydrogen gas. So there are two reactions. Now we will write down the observations. There was no change when the strip of magnesium was put into cold water. On heating, gas bubbles were liberated. So from that, what can you conclude? We can write the conclusion. Magnesium does not react with cold water. Then magnesium reacts with hot water to produce magnesium hydroxide and liberate hydrogen gas. Is that okay, students? So those are the conclusions. Magnesium does not react with cold water. Magnesium reacts with hot water to produce magnesium hydroxide and liberate hydrogen gas. Now what do? We need to write balanced chemical equations, and also you need to identify the type of reaction. So that I will do it as a note. So magnesium with cold water, no reaction. Then magnesium with H2O, but I will write it as hot water. You can write it as a subheading and write it here just to show that it is hot water. So when you write the equation, students, it is understood that it is hot water. And also when they give you the reaction in a paper, then you should know that this reaction is between magnesium and hot water, not cold water. So here the products are going to be magnesium hydroxide and H2 gas. Now what do? We need to balance. Magnesium is balanced. There are 2 hydrogens, 2 plus 2, 4 hydrogens. And also oxygen, there are 2 oxygens. So if we put a coefficient 2 in front of H2O, the reaction becomes balanced. Magnesium balance, 2 to 4 hydrogens. So here 2 hydrogens, 2 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. So the reaction is balanced. Mg plus 2H2O gives rise to MgOH twice plus H2. Cold water, no reaction. Hot water, it reacts, forming magnesium hydroxide and H2. The same way, now I told you all, steam has more heat energy, that is water vapor. Magnesium will react with water vapor also. This is water vapor. Now water vapor is more energy, more heat. So there the product is different. Instead of magnesium hydroxide, only magnesium oxide is formed. But H2 gas is liberated, same as the previous one. Hot water and steam, in both reactions, hydrogen gas is liberated, but when it is hot water, magnesium hydroxide is formed. When it is water vapor, then it is magnesium oxide. Still, we need to check whether the reaction is balanced. Magnesium, 1 each. H2, 2 hydrogens, they are also H2, 2 hydrogens. 1 oxygen, 1 oxygen. So the reaction is balanced. Is that clear, students? So magnesium reacts in 3 different ways. We did not do this activity, but you all have to remember this. With cold water, no reaction. With hot water, it produces magnesium hydroxide and hydrogen gas. With water vapor, there is magnesium oxide and hydrogen gas. So you have to remember these 3 reactions. With that, I will move on to the next one. Magnesium does not give any observable reaction with cold water. But when reacting with hot water, liberation of gas bubbles can be seen. So, liberation of gas bubbles can be seen. If we write the equation again, Students, I am writing the equation over and over again so that you will remember it well. You all also try writing it, balancing it. Whenever you do it over and over again, you remember more easily. Then there will be no confusions for you all. So here we will write the reaction magnesium with water. So here it is hot water. So you know the products are magnesium hydroxide and H2 gas. How did we balance the equation? We put a coefficient 2 in front. So it's balanced. Magnesium plus 2 H2O gives rise to magnesium hydroxide and H2. So that is the reaction. So magnesium reacts with hot water giving magnesium hydroxide and hydrogen gas. That is this reaction. So I have already written the balanced chemical equation for this reaction. Magnesium with hot water. So then if we look at magnesium, magnesium reacts fast with steam. So that is water vapor. The products of the reaction are magnesium oxide and hydrogen gas. Important. You have to remember that. I already wrote the equation for you all. You can remember that. Magnesium plus water, but this is steam. That will give rise to magnesium oxide and hydrogen. So Mg plus H2O, if it gives MgO, that is magnesium oxide, and liberates H2 gas, you should know that it is steam or water vapor. So magnesium reacts in 3 different ways. With cold water, no reaction. With hot water, forms magnesium hydroxide and liberates hydrogen gas. With steam, it gives rise to magnesium oxide and liberates hydrogen gas. I am sure you all can understand that. So with that, students, I will move on to the next slide. So then if we look at other metals, now we are comparing the reaction of metals with water. Aluminium and zinc. Now aluminium and zinc do not react with cold water. So here you have to remember, they also don't react with cold water. On heating in steam, so here heating in steam, they form the corresponding oxide and hydrogen gas. So if you react aluminium with steam, you will get aluminium oxide and hydrogen gas. The same way, if you heat zinc with steam, you will get zinc oxide and hydrogen gas. So if I write the reaction for zinc plus H2O, although it's steam, we write it as H2O. So the products are going to be zinc oxide and H2 gas. Let's check whether the reaction is balanced. 1 zinc, 1 zinc. 2 hydrogens, 1 oxygen, 1 oxygen. So that means the reaction is balanced. And again, this is also a single displacement reaction. All the reactions that we saw, metal with water, they are single displacement reactions. So aluminium and zinc only react with steam. Is that clear? Iron does not react with cold water or hot water. Again, this is iron. It does not react with cold water or hot water. Again, important. Now you can see these, the readiness of reacting with water is decreasing. So aluminium and zinc also do not react with cold or hot water. They also don't react with cold or hot water. Same way, iron also does not react with cold water or hot water. But when heated in steam, again you have to see, when heated in steam, it gives the metal oxide and hydrogen gas. But the metal oxide that is formed is different. When iron reacts with water, it forms Fe3O4 plus it liberates H2 gas. So now I told you all before also students, there are different iron oxides. You are familiar with FeO, you were familiar with Fe2O3. Now this is another iron oxide, Fe3O4. So on reacting with steam, when heated with steam, iron gives rise to this type of reaction. Again, we need to balance this reaction. Check whether it is balanced or not. Now look at iron Fe, Fe3. So 3 ions are needed. H2, 2H2, there are 2H2, no problem. But O, you can see there is only one oxygen here. There are 4 oxygen atoms there. Then what do we need to do? We need to put a 4 here for oxygen. So 4 into 2, 8H2. So this also has to be balanced, 4H2. And also there are 3 iron atoms. So you need to put a 3 there. 3 Fe plus 4 H2O gives rise to Fe3O4 and 4 hydrogen gas. So that is the reaction of iron with steam. So now think students, sodium reacts violently with cold water. So you can imagine how violent the reaction of sodium will be with hot water or steam. Normally we don't try that in the lab. Magnesium doesn't react with cold water, it reacts with hot water and steam. Then aluminium and zinc, they don't react with cold water or hot water, they react with steam. Iron also reacts with steam, does not react with cold water or hot water. Then can you think of the metals like gold, platinum? Will they react with water? No. Again, you all know this. We use gold jewellery. When we want to clean the gold jewellery, sometimes we wash it in warm water with a little bit of shampoo or soap. Usually, we wash it in warm water. There is no reaction. So, metals like silver, gold, platinum, they usually don't react with water. So, again, you can see the difference in reactivity. So, these are the reactions, students. Now, you can see aluminium and zinc, they react with water, that is steam, to produce zinc oxide and hydrogen. Same way, aluminium will produce aluminium oxide and release hydrogen. Here, I told you all this is a slightly different reaction where Fe3O4 is produced, and there is another difference, students. You all have to remember that. Here I have put the arrow, the forward arrow, to show that the reaction takes place from reactants to products. But in real, this reaction occurs as a reversible reaction. So instead of using this arrow, what we do is we use an arrow like that. Half arrow towards the forward reaction, iron and water forming Fe3O4 and H2. Another half arrow indicates that hydrogen and Fe3O4 react again and form Fe and H2O. So the reaction can take place in both directions, the forward direction and the backward direction. So this type of reaction is known as a reversible reaction. Reversible reaction. So that is also another difference. Now zinc and water vapor, that is steam, forms zinc oxide and hydrogen. That's only a forward reaction. But iron with steam is a reversible reaction. It can occur in the forward direction or the backward direction. You all have to remember that, student. With that, I will move on to the next slide. So for extra knowledge, they have given that under extra knowledge as well, 3Fe plus 4H2O giving rise to Fe3O4 and 4H2 gas. There again you can see this reversible arrow. You can see that arrow, students. Pay your attention to the sign, this sign. Half arrows combine together in both directions. In the above equation, it indicates that the above reaction is reversible. That means the products can be formed from the reactants and also the reactants can be formed from the products. So the reaction can take place in both directions. You all have to remember that, students. Is that clear to you all? So again, if we summarize, you know, sodium reacts violently with cold water. So obviously the reaction with hot water and steam will be very, very violent. Magnesium does not react with cold water, reacts with hot water forming magnesium oxide and hydrogen. And magnesium with steam forms magnesium oxide and hydrogen. Whereas zinc, aluminium, they form the oxide and liberate hydrogen gas. Iron forms this type of oxide and liberates hydrogen gas, but it is a reversible reaction. Then if you consider the other metals, silver, platinum and gold, they do not react with water. So with that, students, I will move on to the next slide. So here you can see metals like silver, platinum and gold do not react with cold water, hot water and even with steam. So these three metals, silver, platinum and gold, they do not react with water, cold water, hot water or steam. So foregoing facts show that the reactivity of metals with water varies with the metal. So as I did before, students, to summarize the reactions of metals with water, I will write down a table so that it is easy for you all to compare the reactivities. So I will have the metals here and the three types of water or instances: cold water, hot water and steam. So we will have the metal, cold water, hot water and steam. So then I will have the metal, first metal, sodium. How is the reaction? Violent, fast reaction. Violent, fast reaction. And what are the products? Sodium hydroxide and H2. So what do you think for hot water and steam? They will also be very violent. Very violent. And he also very violent. But we did not perform. Not performed. So same goes for this as well. Because we know with cold water itself it was a very violent reaction. With hot water and steam it will be very violent. So because of that we are not sure about the products. So most probably it can be sodium hydroxide and hydrogen gas, or it can be sodium hydroxide and or sodium oxide and hydrogen gas. So we do not know the products. Then for magnesium. Magnesium, what happened? There was no reaction. Here there is reaction, but what are the products? Here we got magnesium hydroxide and we got hydrogen gas. It reacts but somewhat slow. Then with steam, again there is the reaction, but we got magnesium oxide and hydrogen gas. So again the difference in reaction. We considered the reaction of aluminium and zinc. So aluminium, what happens? Aluminium, no reaction with cold water, no reaction with hot water, but with steam it gives aluminium oxide, and H2 gas, only with steam. We considered the other metal. The next one, zinc. Zinc again, no reaction with cold water, no reaction with hot water, but with steam you get zinc oxide and hydrogen gas. Thereafter, what did we consider? We considered iron. Iron, what happens there? No reaction with cold water, no reaction with hot water, but with steam you get Fe3O4 and H2. And also it is a reversible reaction. Reversible reaction. So here. So then, if we consider the other elements, what are the other three elements? We considered silver, platinum, and gold. So there you have to remember no reaction, no reaction, and no reaction. There is no reaction. So that is how we can compare and easily remember the reactivity of metals with water. Sodium, violent reaction with cold water. It's a fast reaction, gives rise to sodium hydroxide and hydrogen. The other two we didn't try because it would be a very, very violent reaction. Magnesium, no reaction with cold water, but with hot water it gives rise to hydroxide and hydrogen gas. Magnesium oxide and hydrogen gas are produced with steam. Aluminium, zinc, iron, no reaction with cold and hot water, but they produce the oxide and hydrogen with steam. That again, aluminium oxide Al2O3, zinc oxide ZNO, those are normal reactions, but iron, it produces Fe3O4 and it is a reversible reaction. Silver, platinum, gold, they do not react with water. Cold water, hot water or steam. There is one common thing you can notice. What is it? Whenever they react, whether it's cold water, hot water or steam, always metals liberate hydrogen when they react with water. That is important. So here, metals liberate hydrogen hydrogen gas when, or you can say if, they react with water. And if that happens, it is always a single displacement reaction. Single displacement reaction. So these are all the reactions that we wrote. They are single displacement reactions. Is that okay, students? So that is the summary of all the reactions we considered under reactivity of metals with water. So we have already discussed the reactivity of metals with air, that is oxygen, and then reactivity of metals with water. Cold water, hot water and steam. So with that, students, I am going to end this chapter, but in the next chapter, we will discuss the reactivity of metals with acids.